Hi everybody, welcome back to Chem 140. What do we got going on today? We're going to do more Unit 12. Hopefully all of my issues with the tablet have been resolved. I actually went and tested it, and I guess I have to click. And it's like, hooray! I don't know how to spell. It works. Look, I can do things like percent and equals, and it doesn't screw up. And the only thing that I did was I rebooted the computer. Like, I don't understand. Like, what can I do in 2 days that wrecks Photoshop? Oops, I don't want to close it. I mean, I want to, like, stab it because it's driving me crazy. I tried a few other things, and maybe those might be toggles that work. Who knows? Because the version I'm using is old because it's what I have. And I guess it just doesn't like Windows 10. It liked Windows 7 just fine. But who knows? So, again, never update anything, right? What else do we have going on? So, last call for quiz number 5 is tonight. Make sure you get that in. It will close at 11:59. And then quiz number 6 is due tomorrow. It will close on Thursday. So, yesterday we left off our discussion by introducing a concept called the mole, and you can basically summarize the mole, at least so far, as the following. 1 mole equals Avogadro's number of things. I've noticed that whatever setting I chose to disable Windows ink is actually, like, making it a lot more sensitive, which I appreciate. So my handwriting will look a little jiggly, but that's just because of the tablet. So 1 mole of things is equal to this number of things, 6.022 times 10 to the 23, which we said was a ginormous number. So we're going to take huge quantities of things and turn them into moles to represent those same quantities, but just to conceptualize them a little bit better. Now, it helps to have visual examples of that, and so later on I'm going to show some calculations, and you can visualize those things by looking them up online. But I bet I could actually find it really quickly in just a second. So I'm going to do this first example with you. And these types of problems, oops, that didn't capture how I expected it to. These types of problems are going to be just like what we did at the very start of the quarter. Remember when we were converting like feet to inches or whatever, stuff like that? Now we're going to convert atoms to moles. And let me actually, hold on just a second. It's a little blurry if I do it that way. All right. So how do we do that? Well, we know that there are Avogadro's number of atoms in 1 mole. So if I have one of these quantities, either I'm starting with some number of moles or some number of atoms, I can convert to the other thing, just like we had done before. If I gave you feet, you could convert it to inches. If I gave you inches, you could convert it to feet. Same principle applies here. So here's the number that we're starting with. I have this many moles of carbon. And my question is asking you, how many atoms are in that sample? And so what we would do is we just set up our units just like before. I'm going to turn moles of carbon into atoms of carbon because I have a relationship that relates those together. And I'll do dimensional analysis to cancel out what I don't want, leaving only what I do want. And then we'll just run the numbers. How many atoms are in a mole? Well, there's Avogadro's number of atoms in 1 mole. Now, very important, make sure you put the numbers in the right spot. So put the 1 with the mole and the Avogadro's number with atoms. Don't swap them, you'll get the wrong result. And then it's just a matter of punch it into the calculator. So let's do that. 0.256 times 6.022 times 10 to the 23. And I get... I typed in times 10 to the 3. Oops. Hold on. 23. There we go. 1.542 times 10 to the 23. Well, I only need 3 sig figs, so... And there you go. So again, that's a ginormous number of atoms still, even though it's only 1/4 of a mole. Now that's the gist of how to do that type of problem. So let's go back over here, and I'll give you the reverse problem. You could try this one right now. So let's suppose that you have an automobile airbag, and a sensor determines that there are 1.65 times 10 to the 24 molecules of nitrogen in the airbag. How many moles is that? So what I want you to do is convert that number to moles using the technique that I just showed you. So go ahead and do that. I'll give you about 3-4 minutes or so to do it. And then we'll go over the answers together in just a moment. Now, as a hint, you should get a small number of moles, like between 0 and 10, I would say. You should not get something times 10 to the 46. If you get 10 to the 46 at any point in this class, you've probably put the numbers in the wrong spots, so just be mindful of that. Also, use parentheses when doing division on your calculator. Those are just the common places that things go wrong. Let me know if you have any questions, and I'll be back in just a moment. 1 more minute, we'll go over the answer. All right, so I'm going to do this on this screen right here. So I have 1.65 times 10 to the 24 molecules. Oh, that's not what I want at all. Why is this happening? Molecules of N2. I bet it might have been because I hit this button. Is that why? Yeah, okay. I have a button on my stylus, and I try not to hit it because I don't have it programmed to do anything, but sometimes I do. All right, and if I want to convert that to moles, then I just put the units that I don't want out down here, and the units that I do want up here. Now, it's real easy to get molecules and moles mixed up. So again, always, always, always be writing out your units. If you're just putting in the numbers, then you're going to get confused when you have to do this on your own. Because these units and what you're putting where tell you where to put the numbers. So where do I put Avogadro's number? Well, I put it next to the thing I'm counting. I'm counting molecules, right? So I would put it down here. And then 1 mole is that many molecules. Okay, now we just punch in the calculator. 1.65 times 10 to the 24 divided by Avogadro's number. And I got 2.7399, which to 3 sig figs would be 2.74 moles of N2. There you go. All right, so those are some very basic calculations that you can do. Oops, I got to clear it now. Using the mole concept. So I'm going to give you 2 problems to do more practice with. The first one is, again, moles to atoms. The second one is to try and get you to consider magnitudes of numbers. I'm going to give you something that is incredibly small. I'm going to give you a nanoparticle. A nanoparticle has 10 to the minus 11 moles of gold. A nanoparticle, however, still has a lot of particles in it. And so what I want you to do is do that calculation and consider your answer. What is a small number of atoms? Is it 20? Is it a billion? What would small be relative to this nanoparticle? And you'll see that your answer is like, wow, that's a lot of atoms still. So go ahead and do these 2 problems. Type your answers in the chat, and we'll go over them together in 5 minutes. Yeah, 5 minutes. All right, one more minute, and we'll go over the answers here. All right, so let's go over here. Get rid of that. Oh, that's the first problem. Look at that. Okay. So, for this first problem, am I clicked on the right thing? Yeah, okay. I have this many moles of lead. And I want to turn that into atoms, so I'm going to put moles in the bottom to cancel it. And I'm going to put, oops. I'm not going to put moles on the top also. I'm thinking of later calculations here. Atoms of lead. There we go. Where does Avogadro's number go? It goes next to the thing we're counting. That's atoms, right? So, Avogadro's number of atoms per mole. And so I punch in the calculator and I get probably like 5 times 10 to the 23 something, right? 0.835. 5.03 times 10 to the 23 atoms of lead. There you go. And then we can do the opposite problem. But we're going to start with we're starting with a very small number of atoms. Or small number of moles, actually. So this is exactly the same type of problem, it turns out. So I got 5.35 times 10 to the minus 11 moles of gold. And then we'll put the units that we want to cancel on the bottom. We'll turn moles into atoms. No, you don't apply Avogadro's number to whatever. You apply Avogadro's number when you want a number of particles. So, if that's atoms or molecules, then it works the same way, because Avogadro's number is just a count. You are counting individual atoms. A mole is just a collection of them. So, think of it like a conversion between, like, dozen and count. So, like, if I had 12 dozen bagels, that's 144 bagels, because there's 12 bagels in a dozen, right? Same thing here. If I have this many moles, and I know that there are Avogadro's number per mole, like this, Avogadro's number of atoms in 1 mole, I can do the calculation. So I'm punching that in the calculator, and I get 3.22 times 10 to the 13 atoms of gold. That is still a lot of atoms. Like, that's 32 trillion atoms in a nanoparticle. But atoms are really tiny, like we've said many times before. So, even though I have a small number right here to start with, like this is real small, I still get a really big answer because a mole is a lot of things. Now, what does a mole look like? Let's see if I can find some pictures here. Yeah, here's a good picture. So, if we were going to look at what 1 mole of stuff looks like, here's what we could do. So on the screen here, I have various substances, and I've weighed out 1 mole of them. Well, I haven't weighed out 1 mole of them. And these numbers might look pretty random to you. You might think, like, well, why did you pick these numbers? Why 24.3 for magnesium? Why 12 for carbon? Why 65.4 for zinc? Well, there's a reason for that, and these numbers might look a little bit familiar. If you don't have it already, grab your periodic table and see if you can figure out why I chose each number of grams to be 1 mole of the substance that I have displayed on the screen. Why do you think that might be? Where are those numbers coming from? Any idea at all? It's not close to the atomic number. Yeah, there you go. It's the AMU, right? We have defined the AMU in such a way that it is also equal to the number of grams in 1 mole of substance. There might be a little bit of lag on here, unless like I have a setting messed up. Hold on, let me hit edit real quick. It looks okay. Oops. You're not supposed to actually see that part. Let me get rid of that. Sorry, I was trying to figure out if I had set something differently, but everything looked okay. It could just be YouTube today. So, 1 mole of any substance is equal to the mass on the periodic table for that substance. So if you wanted 1 mole of sodium, you would have to weigh out 22.990 grams of it, because that is the number of grams per mole by definition. We have set up AMU to work out that way. So now what that means is that when I'm doing these conversions, I can do things like this. I know how many atoms are in a mole, but I also know how many grams there are in the mole, provided I know what the substance is. Now, this only works for elements and compounds. Obviously, you can't convert moles to mass if you are measuring something like, say, footballs, or cake, or cats. I thought I heard a cat when I said that, but I guess I didn't. So, we can only use atomic masses off the periodic table. And so this is called the molar mass. So you could write the relationship for any element. So if I was going to say, take chromium, where's chromium on the periodic table? 1 mole of chromium is equal to, it's element 24, and this is 51.996 at the bottom, 51.996 grams of chromium. And whenever we're going to write out all of these units, it's real important that you include the unit and the element, or elements if it's a compound. Okay, so don't just write moles and grams, write what the units are. Because there are not 51.996 grams in a mole of generic mystery element X. There are only 51.996 grams of chromium in 1 mole of chromium. So identifying what the elements are is very important for your bookkeeping. Because if you put the wrong number in there because you didn't write the symbol, the whole problem will fall apart, right? And we don't want that. We want to get the correct answer every time. So with that in mind, let's do some practice problems with this. You can look up the molar mass of xenon and uranium. They're just on the periodic table, but I want to actually do some problems with these. Now, this is still true whether it's an element or a compound. If you have compound formula masses with AMU, that must be their mass in grams per mole. So table salt, for instance, 58 grams of table salt would be 1 mole. It's a lot of salt. Don't eat 58 grams of table salt. And so we can do the molar masses of these things in grams per mole, but this is just going to require us to go to LenTech, right? So if you type these things into LenTech, you can get their mass in AMU, and then just scribble out the AMU and write grams per mole. So I'm going to leave these exercises for you to do. You can also look up the compound that I made in college. Yes, I am a published chemist. I have a compound that is in the literature. I crystallized it myself. It's totally useless. But yeah, so let's actually get to the exercises and start doing conversions from grams to moles. Now, this is what we did at the start. We did particles to moles. Note that I'm using the word particles here because it's just too much effort for me to fill in 4 or 5 words in this tiny box. It's much more convenient to just write the word particles. So whenever you see particles, you should think of atoms or molecules or formula units. I messed up. In other words, you're counting something. Whenever you look at particles, if I want you to tell me the count of how many things you have, that's when you use the particles box. Now, if I want you to tell me the number of moles I have, that's easy enough. You just divide the number of particles you have by Avogadro's number. And we spent the first half of this hour doing those exercises. Now, we just talked about that you can also turn grams into moles or moles into grams just as easily. So if the top 2 things can be converted back and forth, and the bottom 2 things can be converted back and forth, we should be able to convert particles and grams back and forth too by going through moles. So if I give you a problem that's like, oh, I have this many particles, I could turn that into moles, and then I can turn that into grams. And likewise, I could go in reverse too. This is like those problems where you had to turn feet into inches and inches into centimeters, where you just had to do a second conversion. So that's what we're going to be doing. However, in the context of the problem, the identity of what you're trying to do is going to be buried in there somewhere, right? How do I know what to turn it into? Well, you have to use critical thinking and contextualize what the problem is trying to ask you, right? So, for instance, if I gave you this problem and I just said, which of these has a greater mass? What would your first step be to do? Well, I gave you moles. What are the units of mass? Ask yourself, what should I do to solve this problem? Which of these has the bigger mass? Well, it should be the one that has more grams, right? Not necessarily more moles, because moles are not a mass, they are moles. So, let's convert each of these to grams. Let me get the red out here. So, if I have 2 moles of oxygen, I could turn moles of oxygen into grams of oxygen by looking up the mass per mole on the periodic table. And according to the periodic table, there are 15.999 grams per mole. Remember that we get that from the periodic table, so you do need to have p-table open. And when I do the calculation, I get that 32 grams of oxygen. Now let's do the same thing for hydrogen. And according to the periodic table, there are 1.008 grams of hydrogen per mole. When I multiply those together, I get 16.1 grams of hydrogen. All right, which one weighs more? Well, this is the bigger number, so this is the answer, right? So those are the types of problems we could do. That's a very simple one. Turn moles into grams. Okay, we did it. All right. How about this one? I get 34.9 grams of iodine. How many moles did I obtain? So what I want you to do is use the periodic table, find iodine, and then do this conversion. How many grams per mole of iodine are there? So how many moles are there in 34.9 grams of it? Okay. I'll be back to check on you in 3 minutes. See you in a bit. All right, one more minute, we'll go over the answers. That was odd. I hope that, like, the stream didn't just go down. It says that I have dropped frames, so hopefully everything is okay. I think I'm back. My headphones got all staticky for a second there. All right, so let's do this problem. Let me know if there are any issues. You're all here. Okay, cool. I just see, like, I think that, like, that might have just been really bad timing because I looked at, I have Steam in the background on this monitor, and it disconnected, and it does this every Tuesday. I just remembered. But at the same time, I suddenly noticed that I had dropped frames, and I think that, like, I jiggled the headset cord when I, like, put it back on or something. I don't know. Let's see here. So I've got 34.9 grams of iodine, and I want to convert that into moles. So I got to put the unit that I want to cancel out down here, right? So we'll put grams of iodine. We'll put moles of iodine at the top. And then we'll go and look up the numbers on the periodic table. And so I have it right here. 1 mole of iodine is 126.90. So 1 mole, 126.90. And again, this number comes from the periodic table. And then finally, we'll just punch in the calculator. So 34.9, 126.90, 0.275 moles of iodine. There you go. So can we say that the AMU of an element is interchangeable with its weight in grams? Yes, because that is actually why we chose AMU to be what it is. This is just sort of a feature that is built into it that we didn't talk about it because we hadn't gotten to the mole idea yet. But we have defined the number of atoms in a mole and the mass of an AMU to be how they were, so we can use these numbers off the periodic table. And the consequences of that are that we just get that weird random number for how many atoms there are in a mole. We could have picked any number of atoms to be in a mole. We could have picked 10 to the 30, and then all of the other numbers we'd have would be different. But if we pick a specific number, we can make this relationship true. And so that's what we did. So 1 AMU is indeed the same as 1 gram per mole. Those are, by definition, the same thing. So you can interchange them however you want to. That said, we don't really need this one. This one's kind of obsolete now. This is what we're going to be using by far the most out of all of the conversions. All right. For this last problem, I want you to tell me how many atoms of sulfur are in this sample with 19.7 grams. And you're going to have to do this in not just one step, but two. So first you got to convert it from grams to something, and then convert that something to something else, and that will get you to the answer. I'm going to let you try it, and then we'll show you how to do it in about 3 minutes. Okay? See you in a bit. One more minute. We'll go over the answers. All right, let's show how we get to the answer here. And then we're due for a break, so we'll do that after this. So, what do you do if you have to go from grams to atoms? Now, the problem isn't asking you to calculate the number of moles, but you need to know the number of moles in order to effectively finish the problem. So if I have 19.7 grams of, what is this, sulfur? To solve this, I could turn grams of sulfur into moles of sulfur. And if I know the number of moles, I then know the number of atoms, right? Because there's a relationship between grams and moles that I can get off of the periodic table. And the relationship between moles and atoms is Avogadro's number. So we just have to do both. So let's do both. So first, I got to cancel out my units. I put what I don't want on the bottom, and then convert to what I do want on the top. And then we can just fill in the numbers if we'd like, or we could just do the next part. I'm going to fill in the numbers for you, but then later on later examples, I'm going to do all the units first. So this is sulfur. There are 32.07 grams per mole of sulfur. Now, if I hit equal on the calculator, this would tell me the number of moles, right? And then I could keep going. But since it's all multiplication, let's just keep the calculation going as is. So we'll just do this. Get rid of our moles here and turn it into atoms. And now we'll fill in the numbers. How many atoms are there per mole? Well, there's Avogadro's number of them, right? Finally, we'll type in the answer in our calculator, or we'll type the numbers in the calculator, and then we will get the answer. This is where you want to be very careful about using parentheses. When you do any division, make sure that you are entering parentheses around what you're doing. There's your result. I got 3.70. It looks like Keegan got 3.69. Those are close enough. You get the same answer to the last sig fig, so it's good. We did the problem correctly. All right, so what we're going to do is when we come back, we're going to have another set of these problems to do. And oops, I hit the wrong thing there. So I'm going to have you try these problems when you get back. You could look at those if you want, but we are going to take a break real quick. So let me put the timer on. And we'll get more music going. I'm just basically playing like old childhood games this week for music. So that's why they're like old and NES sounding and then short. All right. We'll see you in a bit. Alright, we're back. Alright, so... let's see here. I want you to try these problems, if you haven't started them already. Are you tell me how many moles of helium are in this balloon that has a little under half a gram? I've got some benzene that has this many molecules. How many moles of it are there? Basically, I'm asking you a bunch of different problems in various contexts, because even though this section was, oh, I can turn grams into moles, in reality, you're going to be seeing all of these types of problems mixed together. And a practical example of that would be the bottom problem down here. So number 4, if you have a 20-gallon gas tank that contains octane, how many moles of octane are in it? If I give you, instead of a mass, I give you a volume. Well, remember, you can turn mass and volume back and forth by using density. So I gave you the density there. So go ahead and try those 4 problems. I'm going to give you about 6 or 7 minutes or so to do these. If you have any questions in the chat or you have any answers to post, go ahead and put them there, and I will address them. And I'll see you in a little bit. Let's do 2 more minutes, and then we'll go over all the answers together. All right, let's go over the answers. So first I got to do this. There we go. All right. How many moles of helium are in this balloon? Make sure my... Okay, I do have it unmuted. All right, so we have 0.450 grams of helium. And I want to find out how many moles of helium there are. Now, if you're ever stuck on these problems, you can draw one of these little maps like I have over here, just to indicate what you're doing for your units. And then set up the units so that the ones you don't want cancel. And you turn them into the ones you do. All right, so how many moles and how many grams are there for helium? According to the periodic table, I have 4.003 grams of helium per mole. And so when I do this calculation, I get 0.112 grams of helium. Oops. There we go. All right, so that's the first one. All right, so for the second problem, I have a sample of molecules, and I want to know how many moles there are. So I could go molecules of benzene to moles of benzene. How do I do that? Well, since this is a count, I'm going to have to use Avogadro's number for this, right? So let's write down the number of molecules we have, which is this. And then I'm going to convert molecules into moles. Cancel out those units. And then we'll fill in the numbers. Where do I put Avogadro's number? There are 6.022 times 10 to the 23 molecules per mole. And in doing that, I should get the number of moles of benzene. So let's type that in. 5.79 times 10 to the 24. Oops, I hit the wrong button. Divided by 6.022 times 10 to the 23. Enter. And I get 9.614. So I only need 3 sig figs. 9.61 moles of benzene. There you go. Very good. All right. For number 3, I got to capture it on the screen, though, first. Number 3, we need to know the number of molecules of water in a glass containing this much water. So now we're going to do something like, okay, I started with grams. I need to get to molecules. But I got to go through moles first to do that. And these are all H2O. We know how to go between grams and molecules. This uses the periodic table, and this uses Avogadro. So let's do the calculation. I have a drinking glass of water. And I'm going to turn grams of water into moles of water. And once I know the number of moles of water, I could then turn the number of moles into molecules, right? Then I just have to go and fill in these numbers. Okay, how many moles and how many grams are there for water? How do I get this information here? Well, we go back to Lentech, right? So, oops, I'm on the wrong screen. There we go. Let me do that. Let me find Lentech. Where is it? There it is. I think that's right. Yeah. Oh, it's real tiny, though. Hold on. So here's Lentech again. And if I type in H2O, should show on your screen. Oh, it would if I scrolled it down a little bit. 18.02 grams per mole. And you can actually see that even though I was using Lentech yesterday and talking about AMU, you could see that it actually says grams per mole here. So we're going to fill that number in on our conversion here. 18.02 grams per mole. And then finally, how do I go from moles to molecules? We use Avogadro's number. Where does Avogadro's number go? There are Avogadro's number of molecules in a mole. Make sure that you are lining up the number with what it represents. Don't accidentally swap the positions of them. Okay? So it's real important to understand these relationships. All right, and let's punch all this in the calculator. So 355 times Avogadro divided by 18.02. And I got 1.19 times 10 to the 25. So when you drink a glass of water, you're consuming about 10 to the 25 molecules of water. It's a lot of water. A lot of water molecules, anyway. I ran out of space, so you're going to have to pause the video if you still need that. Because I'm going to have to clear everything and go back up to the top here. All right, this last problem, I have 20 gallons of octane, which is C8H18. And I need to know the number of moles. Now, the only relationships that we have for moles are these, right? I can, from the number of particles, which would be like atoms or molecules or whatever. So in this case, it's molecules. Or I could do grams. We cannot do volume to moles. There's no relationship yet. We haven't figured one out. So how do we get from volume to grams? Well, we can do this using the density. Now, if our density is in grams per milliliter, then my volume needs to be in milliliters, right? So I've got gallons. I need to first get it to milliliters. So here's what I did to do this problem. So first, I turn gallons into... You could go directly to milliliters if you use Google, but I don't want to. I'm going to do it the way I know. I'm going to turn gallons into liters. And then I'll turn liters into milliliters. And so when I hit enter on my calculator, that should give me the number of milliliters, right? Now I've run out of space, so I'm going to just hit... Normally I would just keep doing the calculation, but I ran out of room, so I'm going to do this, and then I'm going to hit enter, and we're going to get a number of milliliters here. So how many gallons and how many liters? Well, we've got to look that up on Google. 1 gallon to liters. And Google says that there are 4.546 liters in a gallon. That seems big. This is the wrong gallon, isn't it? Yeah, there we go. Okay. I was using some other gallon. I was like, isn't it like 3.7? Yeah, it's 3.785. So be careful on Google. I typed in 1 gallon to liters, and it gave me the wrong units because it wasn't using the US liquid gallon. So be mindful of that, because that's an issue that could come up. And then how many liters are in how many milliliters? Well, in 1 milliliter, there are 10 to the minus 3 liters. Remember your metric prefixes from Unit 3. It was so long ago, but we're going to use them anyway. And so when I do all this, I get 75,700 milliliters of octane, which I'm going to just move right over here. I got part of the arrow. It's coming with. That's fine. We don't really need that equal sign. It can just go off the side there. All right, so now I'm at the start of my little chain here. I have the volume in milliliters. This is done. So using the density, I could get to grams, and then I could get to moles. And we don't actually need this part. This is just part of the example. So we're going to turn milliliters of octane into grams of octane. And those units will cancel out. And then once I know the number of grams of octane, I know the number of moles of octane. And so now this problem is just like what we were doing before. Okay, how many grams are there per milliliter of octane? Well, according to the right up here, let me see if I can point at it. It should be this right here. Yeah, there we go. 0.703 grams per 1 milliliter. That's how density works, yeah? So this right here, this is the density. And then over here, how many grams of octane are in a mole? Well, we go back to Lentech. So we'll just go boop. We'll just turn that back on. And then I'll just type in C8H18 and hit enter. And it says 114.23. So we'll just write that in here. 1 mole is 114.23 grams of octane. All right. And then we just type it all in. 75700 times 0.703 divided by 114.23. And I got 466, or how many six do we have? Yeah, we get 3. 466 moles of octane. So when you fill your tank, assuming you have my Jeep Wrangler, if you do, I want it back, and it has a 20-gallon tank, which I've estimated that that's probably what it is. It's probably a little smaller. You would be putting 466 moles of gasoline into the tank if it was all octane. If it was a different molecule that had a different density, you'd be putting a different amount. Or if it was a mixture and so on. But if it was a pure substance, that's how much you'd be putting in there. That's a lot of moles, though. No wonder it cost me $70 to fill my tank. All right. Those are just a sample of the exercises that we can do in this course when talking about moles. And we're going to actually do more and more different exercises of varying types as we go on through this set of slides. So let's go to the next section here. So we've talked about molecules and the relationships between grams and moles and number of particles. And we've also done that with atoms. Now what we're going to do is we're going to take formulas and we're going to look at pieces of formulas. For instance, if I looked at H2O, I could say that, well, I've got hydrogens in there, and of that I have 2. Or I could look at oxygen, of which I have 1, and we'll just put a little X there. Now, if I said, okay, I have 1 molecule, yeah, I'll split it into 2 H's and O's. But what if I said I had 1... Ooh, I didn't actually even hit the button that time. What if I instead said I have 1 mole of hydrogen? Well, then you just say, oh, well, then I must have 2 moles of each of these, right? And that's where we're going with this, is we are going to look at a formula and write relationships about the parts of that formula. And let's do that here. So we're going to use this molecule as our example, P2O5. In 1 molecule of P2O5, there are 2 phosphorus and 5 oxygen atoms. And what I'm going to do is I'm going to take that sentence, I'm going to write it out in the following way. So, in 1 molecule of P2O5, there are 2 phosphorus atoms and 5 oxygen atoms. Oops, let me write it the other way around, though. All right. Everyone agree that that equation represents that sentence above. In 1 molecule of P2O5, there are, so that means that it is true that there are 2 phosphorus atoms, and it is true that there are 5 oxygen atoms. That seems all right, yeah? Now, with any equality that you have something equal to something else equal to something else, you pick any two of these and they would be equal, right? So if I only wanted these two, I could say that those are equal to each other. I could also just say that one molecule, P2O5, equals 5 atoms of oxygen, and just separate them into two statements like this, yeah? That's allowed. So now I have two statements that are separate from each other. What I'm going to do now is I'm going to then multiply them by a mole. And I'm going to do that for the bottom statement too. All right, we'll call this statement A and this one B. So A would now become 1 mole times 1 molecule would be 1 mole of molecules. And 2 atoms times a mole would be 2 moles of atoms. And then we could do the same thing for B. 1 mole times a molecule is 1 mole. And then 5 atoms times a mole is 5 moles. And so what we have done is we've related the whole molecule to its parts. So if I gave you 1 mole of P2O5, there would be 2 moles of phosphorus in there. And that makes sense, right? Because this 2 tells you that. And in 1 mole of P2O5, there are 5 moles of O because this 5 tells you that too. Now, if you have those statements, what if I said something like this? I'm going to give you 5 moles of P2O5. And I want you to tell me how much oxygen is in there. How many moles? You say, well, I just times it by 5 because there's 5 for every one, right? Yeah, you would. And here's how you show the dimensional analysis for that. First, you put the unit that you don't want down here. And then you put the unit that you do on the top. Notice that the identity is now important because we're doing moles divided by moles, but this one cancels out with this one, which is what we want. And this is why I've been telling you all along, make sure you write the identity, because when we get to this part, which is right now, it will get very confusing if you have not been putting the molecule identifiers on there. And now we just fill in the number. So for every 1 mole of the big thing, P2O5, there are 5 moles of the little thing. And now I can do the calculation. And there you go. That's the expected answer because it should be 5 times what we started with. So these are the types of calculations that we're going to work on in this section, where you're going to make relationships and then work with moles. And then later on, which we're going to do on Wednesday, before we talk about the lab, because the lab is basically what we're doing here. What we're going to do is we are going to say, okay, well, we don't normally work in moles. So if I start with grams and turn it into moles, then I can do this calculation. And then I can take this result and turn it back into grams. So today we're going to work on this part. And then this part will be Wednesday. All right, so let's try this out. I'm going to give you 2.50 moles of P2O5. And what I want you to do is tell me how many moles of oxygen atoms are in there. And once you've done that, do another problem here. How many moles of phosphorus are there in there too? So do 2 calculations, because we just did an oxygen one. Try a phosphorus one. Tell me the answers you get in the chat, and I'll be right back in just 2 or 3 minutes, we'll say. All right, 1 more minute. We'll go over the answers. All right. Oops, hold on. There we go. All right, so how many moles of oxygen atoms are in 2.50 moles of P2O5? All right, so we know that in 1 mole of P2O5, there are some number of moles of O, and that number is right here, right? So in one of the big things, there are 5 oxygens. And what am I calling this? Oh, there we go. We can do the same thing. Oops. There we go. But this time, I want to do phosphorus. Well, how many moles of phosphorus are there per mole of big thing? Well, in one of the big molecules, there are 2 phosphorus. And then we just do the calculation. 2.5 times 2 is 5. And there you go. All right. How many moles of carbon are in this thing? I don't actually know what this thing is. I just wrote a formula. I'm sure that I got this from some molecule I was thinking of at the time, but looking at the formula on its own, I can't think of it. So, how many moles of carbon are there in 1.2 moles of C3H6O3? Go ahead and do the calculation just for the carbon, because we have another problem on the next slide. Or actually, we have another problem on this slide. Type your answer in the chat when you got it. All right, one more minute. We'll go over this answer. All right. So we've got this many moles of our molecule. Oh man, my throat's all scratchy. There we go. I'm sitting here chugging water, so I don't know what's going on. And I want to figure out how many moles of carbon are in the here. So if I go moles C3H6O3, moles of carbon, how many carbon are in the big thing? Well, it's right here. In one of the big thing, there are 3 moles of carbon. Oh, I just want to write carbon there. There we go. So there's my answer. That got in the way, so we'll just leave it there for a sec. All right. I'm going to skip this last problem because we are kind of out of time. But what you would do for a problem like this, where it's asking you how many moles of atoms of any type, is you would make a relationship like this. For 1 mole of C3H6O3, how many atoms of any type are there? Well, there are 3 C's, 6 H's, and 3 O's, right? So I'd say, okay, how many atoms are there of any type? Well, there are 12 total atoms. Or I could say, in 1 mole of this, there are 12 moles of atoms. And then I could solve the problem. So you should just get this number times 12. I'm not going to ask you a problem like that. But just in case something like that came up on, like, I don't know, another class or whatever, you could think about this in whatever type of scope you want. All that we're doing is we're just making relationships that are valid with each other. I'm going to put this problem on the screen just real quick because we're out of time for the day. But you could do the same type of problem here. So I have deoxyribose. This is the sugar backbone in DNA. And this question is asking you how many moles of each type of atom are in a 0.377 mole sample of deoxyribose. So you could do that. You've probably figured out that all you have to do is multiply it by these numbers right here to get the answer. And that's totally right. But I'll leave that as an exercise for you to try on your own. All right, so when we come back tomorrow, what we're going to do is we're going to finish Unit 12, because there's a little bit left to do. And then we're going to jump right into the lab, because the lab is basically Unit 12 and Unit 13. On Monday, we're going to do Unit 13, but by me starting to explain the lab to you, you'll understand what Unit 13 is when we go over it on Monday. I do want to thank everybody for coming out to the lecture. Make sure to get quiz number 5 in tonight, because that's last call. There should be an email going out in about 30 minutes. And then quiz number 6, that one is due tomorrow. It closes on Thursday. Have a wonderful rest of your evening, and I will see you tomorrow for the rest of Unit 12. Take care.